There was a question this morning about how can we use new technology to improve maintenance and extend asset life, and hopefully the next three presentations will provide a bit of an answer to that. So yeah, good afternoon everyone here and everyone who's watching online, and thanks for sticking with us. It's been quite a long day, but quite a good day. So I'm going to talk about crossings now, and there was a question about narrowboating. So it's been quite a long day. I was at this point thinking, do I talk about boating, people ready for a change, or about crossings? But maybe I need to stick to the subject and talk about crossings, but we'll save the boating for another day. So I'm going to talk about, talk about cast crossings, and then I'm going to talk about alternatives, two particular ones, UHPC and COGEX, and I'm going to touch it on movable point crossings at the end, just before I run out of time. So a bit of background on cast crossings for a start. A few terms that are used: AMS, austenitic manganese steel. The austenitic is the metallurgy form in the castings. So it's a manganese mix of steel, lots of different elements in there. So I'm privileged to go to the manufacturers and see how these things are made. Some of you may have visited South Queensferry. But it is, literally a casting. There's a pattern. It gets moulded in sand. Molten metal is poured in there. The as-cast crossing is very brittle, and it gets heat treated, and that's when you get this austenitic structure. And then the casting is machine finished and legs welded on. So cast crossings have been around for many years. So I found an old Edgar Allan O&M manual. So they claim that manganese steels have been around since the 1880s. But certainly in my recent times, looking at BR research papers from the 1980s and early 90s, there was a lot of work, and I think that's when cast crossings were rolled out more widely. The early crossings had fish-plated joints. There was something called the Titan crossing. I think we've still got a few of these in track. So this was an Edgar Allan product, a weldable steel. This was bayonitic, so a different type of structure, different type of material, so not AMS. As time moved on, then composite welds, tri-metal welds as we call them, were developed. This did away with a lot of the fish-plated joints we see on cast crossings, took away one of the common failure modes. And this was because you cannot weld a rail to the austenitic manganese. It's not physically possible, so there's this intermediate stainless steel insert in there. So as time's gone on now, AMS with composite welds, that's become our standard, and in the past 10 years or so, explosive depth hardening as an option. But I think basically I'm just trying to say not all cast crossings are the same. That there are different ones around. So a couple of pictures there for anybody who doesn't know what we're talking about. On the left, it's the tri-metal weld, the composite weld, and a typical modern crossing on the right there. So cast AMS crossings, I mean, they're a good product. I'm not here to knock them at all. The material is very tough. Despite what people sometimes try and tell us, the crack rate is actually very low. So if we get a crack, we can normally do something about it. You can cast them into all sorts of shapes. And I mean, definitely, if you think back sort of 20, 30 years, they replaced a lot of fabricated crossings, and, they're a lot more durable. But they do have some disadvantages. Why look at other things? And I mean, I couldn't get through the door this morning before I was having a conversation outside with some TMEs about cast crossings and all the problems. I know it's a big area of concern. So they do have a low fatigue strength, which is why they crack. Tri-metal welds can fail. And you need a pattern for every crossing. I did a secondment recently with the supply chain team, and crossing patterns is certainly a hot topic. And they can't be ultrasonically tested, so it does rely on people going out and actually looking at the crossings, looking for cracks. So just a little bit of science there. So this is something in the cast crossing standard, an SN curve. So it's the stress range, so this is a stress because when the crossing is in service, it bends. So the maximum sort of bend down, compressive to tensile, and the number of cycles. And I mean, the science is basically the higher the stress range, the less time it lasts. But so when you look at a range of materials, the austenitic manganese has a relatively low threshold. So this kind of flat line area and this slope here. So if you can stay below this stress here, the crossing will last forever. But in reality, we get into this zone here, so the degradation rate reduces, and when we've got excessive voiding, for instance, and the stress range increases, then we end up on this slippery slope, and that's a slippery slope to failure and a crack crossing. So that's the kind of reality that a lot of people know. So we've done quite a lot in recent years, and I say we, you know, myself, a lot of our colleagues, and a lot of the suppliers have worked with us on this. And you know, we'll still talk about top, middle, and bottom. So the top, we improve the profile. There's some work going on at the minute with the R&D team and the universities, always trying to improve the profile of the crossing to reduce the dip angle, reduce the impact force. The middle, redesigning the casting, trying to reduce or remove any stress raisers. And there's a lot of work, again, R&D funded that went on in recent years. A lot of the manufacturers have done work as well to change the design, but then update all the patterns. It's been a big piece of work. So a lot of the cast crossings that you will be buying today are very different from the crossings you bought 5 years ago. They've been through a redesign process. And then the bottom, this is about the support really, because if you don't support them properly, they're not going to last. We can do all of the other good stuff, but this is, you know, it's part of the deal. So we can do some of this through technology. Underbearer pads, I'm a big fan of those. NR60 SNC, it's a more robust design, offers better support. But there's also a lot of work going on at the minute trying to understand support. So we saw in Gal's presentation earlier the devices that sit on the bearers and give us the deflection, the movement on the bearer, support stiffness. So a lot of work trying to go and look at that, trying to relate that to crossings that have had problems, and then try and understand the different treatments that can help to improve. So talking about patterns, there's a lot more in the supply chain side, a lot more standard patterns out there in the industry, but it's a Pareto type arrangement where about 80 patterns account for 85% of the crossings we buy each year, but there are a further 1,500 patterns. Most of these are held by Progress Rail. So when you're looking at pattern improvements, things like that, then there's a big imbalance. So talk about alternatives then. So one thing to mention as we go past that there's the compact 1400 crossing. This has been around for some time. This is a machine nose block crossing, chrome vanadium V. It's been around since 2009, but there's been some work done in the past few years to introduce premium rail for the wing rails and also to optimize the profile of the nose. But it's not something that is going to replace cast crossings, and it's a different footprint. So from challenges, supply chain wise, so yeah, a lot of challenges here. Reducing the reliance on patterns or relying on suppliers who've got the patterns would be a good idea. And technically, it's something that we need to try and match the performance of cast crossings, but talked about some of the disadvantages. If only we could have something that addressed some of those issues as well, that would be good. So two things I'm going to talk about: the UHPC. I'm not going to tell you what it means because they call it ultra high performance crossing. That's what the manufacturers call it. So we just move on. Made by Voestalpine. So what is it? It's a three-part crossing, but the wing blocks and the V are made from a premium steel and are welded on. So a little bit of spiel here about it. So a three-part machine crossing. So these are really premium steel blocks. They're hardened. It's something they've been working on with Deutsche Bahn. The Germans never really got into cast crossings. They didn't think they were a good idea, so they've gone down this route. So the fatigue strength's very high. The wear resistance is very good. You know, what we're told, this is really, really good. It does away with the tri-metal weld as well. It has a much better fatigue strength than our cast crossings that we have at the moment. And we've got one on trial. So there's one been installed at Easter at Witham on Anglia Route. So we're going to be watching this very carefully with the manufacturers and the route team. And we'll see how we go. You know, there's more to do. And there's not just one, but there's two. So the second one, Kojak, so Voslo Kojifer have got a very similar product. So this, rather than being made out of 3 parts, is a single piece. So this is just like a cast centre block. So we refer to it as a machine centre block. You know, something new. So they've got joint venture between themselves as the SNC manufacturer with a steel company, ArcelorMittal. And they've been working on this over many years, different variants. They've used them in tramways, but they've now got something that's really good for mainline rail as well. So this is literally machined from a big billet. You can see the billet there in the factory. And where we're going with this stuff, it's the more complex crossings. So the image on the left there, that's on the Manchester Metro tramway. So Manchester Metro link. So it's a diamond crossing, and that means it gives us the ability to make these kind of crossings without a pattern. So when we get double junctions that are special now, it's 6 or 7 brand new patterns. Anybody who's involved in renewals, that's a lot of money just buying the patterns, but it then ties us into that one manufacturer forever, pretty much, for maintenance and everything else. So this would give us the ability, give us more flexibility. So yeah, Kojaks. We've put one of these in at Chesterfield, North East route. So again, part of a renewal. So again, we're watching this carefully. So yeah, next steps for these, UHPC and Kojaks, monitor them during the trial period. The initial trial phase, we've literally put standard crossings in that if we get a problem, we can put a standard cast crossing in its place. But the second stage will be to go and look at some of these more special crossings, non-standard crossings, and use them more widely. So just before everybody says, great, let's forget cast crossings and have these instead, well, we need to just make sure they work first, that they do the job. But you know, the supply chain at the moment isn't set up to make these in high volume. And anyone who has a cast crossing foundry, you know, they'd have a price on my head, I think, if I was trying to effectively do them out of business. So yeah, it is something we need to use appropriately, and we need to monitor. But it's certainly a game changer in the future. But it's not something that's going to change overnight. I've about run out of time, so we could talk a lot more about swing nose crossings, about switch diamonds, movable point crossings. So, you know, we are doing work on this as well, but I'll have to save that for another time, and I will hand over to Jaydan. I didn't think I had.
Hopefully it'll be on in just a second.
Broken it.
Sing a song, Jaydan? Oh, I don't know any I think you'd like. Right. I have a feeling it's seconds away. Right. So, there we go. Right on time. So I want to talk to you all about the redevelopment of Modular SNC. So, does it go? So I am a keen reader, so I like to have the contents at the start of all of my presentations. So you can see all of the things I'm going to be talking about today. First of all, we need to understand why we have modular and why we continue to use it. We need to understand what has gone wrong with it and how and why that has caused us to do any development work, how we've gotten to the product that we currently have chosen, how we install and monitor it, how the installation at Reading went, and then what's next. So first off, the modular use case. So modular SNC, initially when it was being brought in, it was discussed that you wanted to reduce the time associated with your installation, you wanted to reduce cost in terms of access, you wanted to reduce access requirements overall. And I don't think modular SNC has been 100% successful in achieving all of those aims. But part of the conversation that John had earlier today was that access is getting more and more difficult, and there are definitely locations where you want to do an SNC install where it will be very difficult to do it without using modular SNC. And as you know, It allows you to do this by letting you transport the SNC in panels on tilting wagons. So if your modular doesn't fit on a tilting wagon, you can't really call it modular SNC anymore. So that moves us on to what has gone wrong with the existing modular. Now, neither of those pictures look particularly great, but first of all, we should start with the derailment at Lewisham or Courtauld Junction. So we got some recommendations from the ORR that essentially asked us to go and look at our modular SNC, and we did that, and we've closed those recommendations. However, if this project just stops and doesn't go ahead and we don't do any development, it is still quite likely that those recommendations will be opened and we'll be asked to do it anyway. And as you can see from those pictures, you get issues of wide gauge, you get screws loosening and shearing off, which means you then have to go and do a costly replacement with a supplier. And you can also have twist-related issues. You do tend to have a massive range of between routes and regions of how much of their modular SNC actually has an issue, but that is to be expected. We've heard lots of conversation today about how different the different routes and regions actually are. So it does make sense that one will say every single modular unit they have is a problem, and another one might say that it's only the odd one, 5% or so, likely to be their highest speed or their highest tonnage differential over their modulars. So what have we done so far? Because we've not been sitting on our hands, I can promise you that. First of all would be the introduction of the modular standard 3406, which comes in 3 modules, and it details how to design, how to install, and how to maintain your modular SNC. If you take a look at that image there, it specifically states that what you don't want to do is have back-to-back spine panels, which is where the short end of the bearer of your modular SNC swaps over a span of one bearer. You are more likely to develop a twist fault with that particular design arrangement, which is why you can't do it anymore. And in addition to that, we've had some other changes for install methods, so you can no longer use a bance to torque down your screws, and now there is a specific order that you need to go and torque your screws down. That will reduce the stresses that are going through your screws during installation and try to give you a longer life of your SNC. So how did we end up choosing our new product? So we had lots of conversations with industry experts. We spoke to people in maintenance, asset management, and the installation teams. We also went out to market to see what was on the market. And what we learnt was that the philosophy that Network Rail uses, it's only really Network Rail that uses that philosophy. What we try to do is we try to simulate a long concrete bearer by having a fairly rigid connector between the 2 modular ends. What the rest of the world seems to do is to allow some flexibility. So we've decided to go with a joint that has some flexibility. And as you can see in that diagram there, it shows that when a train goes over one end with our normal arrangements, the wavelength is quite condensed on one side and it spreads out throughout the length of both of your bearers. And that means you get a settlement difference. And because it's trying to act as one long bearer, it doesn't like that settlement difference. But the new joint, the one that we have decided to go forward with, spreads that load a lot more equally across both ends of the bearer, and it also gives you a degree of movement between both sides of your track. And by doing that, you're less likely to have your parts and components break, which means you don't need to go and repair and maintain them. You still will need to, however, go and maintain your track, but that's what we do, we maintain track. This joint has been designed specifically to deal with differential settlement, which we believe is causing a lot of the issues in our modular SNC. And the screws and bolts in this joint have also undergone a Juncker's test, which is a vibration test. Another case where it's been designed specifically for the use case that it has actually been used for. It's also not a new product that's just come out of Lab Factory. It has been in use since 1994, which is coming up to 30 years. And in Network Rail, we started doing modular SNC roughly in 2006. Again, the reason we didn't go with what the rest of the industry was doing was because we were trying a different design philosophy, trying to simulate rigidity. But in using this particular manufacturer, we have almost 3 decades worth of experience. We have 40,000 units installed across the world, Europe, Asia, America, as of 2019. So they have a lot of experience which can help us try to navigate any issues that start to pop up if any issues start to pop up on ours. So that then comes to installing and how we do our monitoring. So the way you install this joint is going to be quite different to historically. First of all, you only have one bolt that you're going to need to torque down. Instead, one bolt on each side that you need to torque down instead of 4 on each side, or 8 in total. Now, using a torque gun to torque these down can actually take quite a long time. So by only having one that you need to torque, you've got essentially a 75% time saving, which is quite big when you consider you can have up to 33 of these joints in a single E-switch, or C-switch even. So you've also got quite a few more components, and the intention going forward is to attach these components together so you can just slot them on without having to fiddle with as many parts as you do. And then there is a little bit more of a challenge when you're looking at lining and leveling, but I'll come on to that in a little bit. Then it comes on to how we do our monitoring. So in addition to all of your standard measures, your first week where you go and inspect, you take gauge, you take all of your readings, and you're doing that again every 2 weeks or every 5 weeks, depending on what you've decided the risk is, we've also decided to put Connex monitors on all of the crossing noses. So that means we can see voiding and displacement, along with any impact loading on our crossing noses every single day throughout the install life of this product. And what that has shown so far is that it actually looks quite good. So we also want to do some more installations of standard or regular modular SNC, so we have something to compare it with, but that part is still going to be ongoing. So that brings us on to doing the delivery at Reading West. So Reading West was NR60 Mark II. It is a C-switch with 60 miles per hour on the through and 15 on the turnout. It does have quite a lot of tonnage going through there, so this was an ideal site to actually put the joint through its paces, see whether or not how it settles under differential, how it settles under quite a bit of load. So I've decided to skip day one because day one was just a Kirov crane putting down the first panels. It's not as interesting as day two. Day two is where you actually have to line and level so you can get your joints to fit. And as you can see in that top photograph there, if the joint isn't lined and it's not leveled correctly, they just won't sit. It won't sit and you can't connect them up, which is quite different from the existing joint, because with the existing joint, if you don't have the level between your two bearer ends completely correct, you can just go and tighten up your screws, pull up your bearer, and then pack afterwards. But that introduces the problem of putting stress through your screws. If you try to do that with this particular modular joint, it will sort of seize and stop moving. So eventually you'll still have to lift that bearer, pack it, and then go back and retorque. Otherwise, it won't look nice and lovely as it does in that second picture there. Day three was something else a lot of people have been concerned about. It is tamping of this particular joint. So this joint only allows you to have a maximum of a 15mm gap between your bearer ends when you are doing your tamping. So there is a bit of a concern that if you can't get your standard tandem tampers, or you can't get your tamper with a third lifting arm, you're not going to be able to do tamping through your SNC. I'm not going to recommend that you use a plain line tamper and you lift the adjacent road via lifts and slews. It can be done, but it's just not the preferred method, and it's not the existing guidance inside of the standards anyway. So fundamentally, there's no difference or no change between what the guidance is for how to tamp or stone blow with this particular SNC. So that brings us on to what's next now. We've done an install, and this went in Reading 6 weeks ago now. First things first, our Connex monitors are showing that it's flat as a pool table. There's limited or no vertical displacement, or 0.7mm, which is the maximum on all 4 of the monitors, and their vertical acceleration is also very low, of 0.2 G. Now this was taken 2 weeks after, but it is still roughly exactly the same as it is now. However, these photos don't look quite as promising. So what these photos show is that there has been some longitudinal movement inside of these joints between roughly Saturday just gone and the day it was installed. Now this is still under investigation, but I can say, having been to site myself and taken measurements, there are no gauge issues here. There are no track faults. It does come across at the moment, if this just does appear to be what just looks like it just looks unpleasant. There's very limited risk, and it would take a lot of movement. I don't think that it would move enough for you to have any issues with tight gauge. but we're still going to go and determine whether or not the cause of this movement could be due to tamping, could be due to stressing, could be due to train movements. So once we determine what this movement is, we'll go and probably take some photos and see if there is any more movement, and if there is no more movement, this may just end up being a feature that you need to watch out for, but not something of concern with this joint going forward. So following on, how do we get to full approval? Again, we need to monitor any issues like the longitudinal movement to see if anything else does pop up, and we need to understand why it does pop up. We need to understand what the best installation procedure is, so we can give that guidance out to anyone who's going to do those installs. And we need to update standards to account for the new joint and for any different processes. And we also need to install an inspection regime for modular going forward, so you know exactly what you need to look for and how you're going to go and look for those. Last thing I would do is I'll give thanks to all of the teams that made this installation happen. Network Rail, the TA, the Western and Wales region, Southern Rail Alliance, Bostock Internet Technology and Connex all played massive parts in bringing this particular modular joint to install. Questions, but I think that's for a little bit later. Thank you.